I just would like to welcome everybody to this Earth Science and Engineering Departmental seminar for this week. And we're totally delighted to have Dr. Robert Pappalardo from JPL. I'm not going to say very much, but basically Bob is the project scientist for the NASA's Europa Clipper mission, which is what he's going to be talking about in this seminar. So we're absolutely delighted that he's been able to join us. There's a lot of interest in planetary science in our department, also Imperial anyway. So just in terms of Bob's CV, if you like his background, he has a BA in geological sciences from Cornell and a PhD in geology from Arizona State University. So our geologists, please note, with a geology degree, you can end up running a mission to the moon of another planet, which is really exciting. And I am just going to turn it over to Bob.
Thank you so much. My regrets for the technical difficulties, but I'm so excited to be here virtually. At least the plan was for a visit this week originally, and while those plans are thwarted, I'm happy to be able to present to you some of the excitement of NASA's Europa Clipper mission to Europa. Some of you may know about Europa, for some it may be new, so I'll give a brief overview of some of the exciting science of Europa, and then we'll turn toward the Europa Clipper mission and the kind of thing that it is trying to do. Okay, Galilean satellites of Jupiter were first seen close up as Voyager spacecraft. This spacecraft flew through the system back in the late 70s. Then it was the Galileo spacecraft, 95 to 2003, that orbited Jupiter, and with every orbit, with a couple of month interval, it would fly by one of the large Galilean satellites of Jupiter, the moons that Galileo Galilei first saw with his primitive telescope and realized that that the sun was not the only center of motion in our solar system, but that these points of light orbited around Jupiter and were moons of Jupiter. Europa is has a skin of H2O, as we'll see. It's intermediate in rock content between rocky Io and Ganymede and Callisto, which are kind of half ice and half rock. See, make my slides advance. There we go. This is just a summary of what Europa's surface looks like. It's relatively sparsely cratered. You can see Pwyll there, or Pwch if you're Welsh, or some of you there maybe and could pronounce it better than I. That's about a 20 or 25 kilometer impact crater, but the sparseness of craters tells us that the surface age of Europa is only about 60 million years. So something has repaved, processes have repaved Europa since the time that dinosaurs roamed the Earth. In the upper left, you can see the ridged plains of Europa. Bizarre cross-cutting ridges and grooves make up the bright icy plains. The dark mottled areas, some of them are chaotic looking, as in the upper right inset, and some of them we see these spots, pits and domes and spots, like in the lower right there. Those spots are about 7 kilometers across. We'll come back and talk briefly about these processes at Europa. What makes Europa so special is that we think there's a subsurface ocean in there, and on Earth, where there's water, there is life. But also, let's see, that ocean is likely directly in contact with mantle rock below. So Ganymede and Callisto might also have oceans, but their thick H2O layers imply that the ocean is sandwiched between ice one above and higher density phases of ice below.
Bob,
Bob,
sorry to interrupt. Your slides have disappeared.
Okay, so what happened is another screen popped up when recording started. Maybe I have to hit share again. Let's do that. There we go. Okay. You can see again, hopefully?
Yes, you're back.
Okay, good. There we go. And there my movie's running. Okay, so we can see in the illustration that Europa's H2O layer is something like 100 kilometers thick. We think the ice shell is something like 20 kilometers thick. So on the left is roughly to scale, with rocky mantle and iron core below. Well, how do we know the interior structure? From gravity data from the Galileo spacecraft. As it passed by Europa, we track its signal. From the Doppler shift, we can get an indication of the axial moment of inertia of Europa that tells us it has a central condensation of material. And so if you assume a 3-layer model, you get about 100 kilometers of H2O. But the gravity data doesn't tell us anything about whether it's liquid. That comes from, as we'll see, the magnetometer data, but also from modeling of the amount of heat input from tidal heating of Europa. On the right is an illustration, not to scale, of Europa. As it orbits around Jupiter, it gets closer and farther. It's somewhat eccentric orbit. And when Europa gets closer to Jupiter, it stretches out from Jupiter's gravity. When it's farther, it compresses back. And it's also librating, rocking back and forth, facing the empty focus of its orbit. And so this tidal kneading creates heat and enough to maintain an ocean beneath its icy shell, likely on the order of 20 to 30 kilometers thick, based on the theoretical modeling. Most of the tidal heat, as well, or at least tidal heat, is input in the icy shell, at the base of the icy shell where the ice is warm. Some amount might, there might be some amount of tidal dissipation in the rocky mantle, but we're not sure. It depends on how warm and deformable the mantle is. So if the mantle's always been warm, it can stay warm. If it's been cold, it's harder to heat it back up again. I mentioned the magnetometer data. That's really the best evidence for an ocean at Europa from the Galileo spacecraft. On the left is an artist's illustration of Jupiter's immense magnetic field and Europa orbiting through it. In the right is a beautiful animation done by Corey Cochran here at JPL, showing how Europa is orbiting Jupiter as Jupiter is rotating with its 10-hour period. Jupiter has a tilted dipole magnetic field, tilted about 10 degrees. So as Jupiter rotates around its axis, the magnetic field is flopping about, so that Europa finds itself alternatingly above and below the magnetic equator of Jupiter. And so Europa is feeling a magnetic field of Jupiter that alternates on a 5.5-hour period, half the synodic period of Europa around Jupiter. And so what's at Europa, there's this magnetic field that's flipping in tandem with the Jovian field. And there's a vector there showing how the Europa field is flopping, swinging in response. So Europa doesn't have a dipole field. Europa has an induced magnetic field that's responding to Jupiter's external forcing. That tells us that Europa must be conductive. Europa's interior must be conductive, and constraints on the depth of that conductive layer are consistent with a salty subsurface ocean some tens of kilometers below the surface. The core is too far away to account for the signal. So it's really the magnetic field evidence that's the best evidence for an ocean at Europa. So if anyone has discovered an ocean at Europa, it's Margie Kivelson, pictured in the upper left there, along with Christian Krana and Xinzhi Jia, representing the next generation, and exploring Europa's magnetic properties. With the Clipper spacecraft, we will make, instead of the dozen flybys of Galileo, we'll make about 50 flybys, from which we can get at much smaller variations in the induced magnetic field to get at not just the period of Jupiter's rotation, the 11-hour period, but the induced field related to Europa's orbiting of Jupiter at an 85-hour period. The illustration upper right is showing the induced field at those two frequencies, blue the 11-hour, red the 85-hour, and knowing both where they cross, we can get at not just the existence of an ocean, but its depth and its conductivity. So there'll be a significant error bar there, but we're going to be able to constrain Europa's ocean depth and conductivity to help us get at the habitability of that ocean, because conductivity then translates into salinity. This is an illustration of Europa's surface from Galileo, high-resolution data inside lower-resolution data, painted with lower still color data. And these double ridges cross-cut Europa's surface. They're the most common feature, yet they're extremely poorly understood. You can also see the background array of fractures. What I think has happened here is that something has pushed up to create these ridges. You can see evidence of mass wasting with boulders, talus at the bottom of this ridge, and indications that there's been upward deflection. But there's an array of models to try to explain these ridges that might, some that induce, that propose eruption along them, some that suggest, whoops, show it from afar there again, some that suggest compression, some that suggest extension. So, but what I think the geological evidence points best to is pushing up from below, as if by warm diapiric material. How could that be? Well, the tidal stresses at Europa will allow the surface to move in a strike-slip fashion, actually back and forth as Europa orbits around its 85-day period. And that motion can create frictional heating along pre-existing fractures that might form from the tidal stresses as well. And that may allow ice to well up in those areas and might even create localized melting. So it's just one model, something we need to test with Europa Clipper. And I haven't even touched in this talk the global pattern of Europa's fractures and how they might be related to this tidal stressing and to longer-term secular stresses on Europa's surface. On the left, there's an illustration of one of Europa's bands. These are areas where the icy crust has completely pulled apart, somewhat analogous to a spreading center on the Earth. So if you cut out that band in Photoshop, you can stick it back together and pre-existing structures will actually match up. So something has pulled apart the icy lithosphere to expose the asthenosphere, the warmer flowing asthenosphere below. I've been working with JPL scientist Sam Howell on trying to model this, and he has used the relatively new sister code, finite difference code, to illustrate how bands may form at Europa. He's illustrated the reds here are colder and stiffer, higher viscosity. The blue are warmer, so starting out with a linear thermal gradient through the ice shell. So you're looking at the surface down to the base of the ice shell. Here, assume 25 kilometers thick. We're gonna look through, I think it's 1 million years here in this illustration, when he pulls the model apart. So you can see faults forming at the surface along shear bands. The base, the icy asthenosphere is convecting, and some of that asthenospheric material is then able to be exposed at the surface in one of these dark bands. As the surface is literally pulled apart, stretched, and pulled apart here in about 1 million years' time in this illustration. So Sam has been able to speculate regarding the morphological range of bands on Europa and even on Ganymede may relate to the strain rate of stretching of the surface to create these bands. go to the next slide. There we go. So there's a lot of evidence of Europa's surface pulling apart to form these bands, but not so much evidence of the surface pushing together. Does Europa have compressional tectonics or subduction zones? Well, there's a process that's been termed subsumption. Kattenhorn and Proctor have come to the conclusion that some features on Europa's surface will flash back and forth might be areas where the pre-existing surface has disappeared. So in reconstructing portions of Europa's surface, they find missing area and suggest that those might be areas where icy lithospheric plates have shoved down and into Europa's warmer asthenosphere. So they're pretty tough to recognize, except when you do a reconstruction of the region and find there's missing terrain. So they consider that the subducting or subsuming plate may simply dissipate by thermal equilibration into the icy asthenosphere below. And again, working with Sam Howell, we've been modeling just that as a function of the convergence rate. It's actually very difficult to shove a cold lithospheric plate into Europa's asthenosphere and get it all the way down to the liquid water ocean. Much more likely that plate just dissipates away as it thermally equilibrates. Here's an array of Europa's impact structures. We talked about Puch in the upper left there. Mannanen is another. There was just recently a paper about Mannanen suggesting there might have been, after the impact, a liquid lake temporarily below the surface there. Govanen at top is more of a typical impact crater, so small craters are more typical. The 20-25 kilometer scale craters of Puch and Mannanen appear to have relaxed upon impact. That suggests that the subsurface of Europa is warm and the impact was able to relax quickly upon formation. Callanish and Tyre are multi-ring structures. When you get to features that are about 40 kilometers across the inferred original crater size, there are only these two that we know of. It's thought that the impact went all the way through the ice shell, and then you have essentially a hole with water below, and that filled in quickly, dragged that cold icy lithosphere along to form these ring fractures, to make these multi-ring structures that we see. We saw evidence of dark stuff, especially in bands at Europa. What's that dark stuff is an important question because it might tell us about the composition of the ocean below. And based on infrared spectra from Galileo, we know there's bright ice-rich stuff. Ice has characteristic absorptions at 1.5 and 2 microns in the near infrared. And there's some dark stuff mixed into that. On the right is an array of lab spectra of candidate materials, salts, magnesium sulfate, epsomite is a candidate. Sodium chloride is a candidate. Sulfuric acid has been suggested, and it may be a combination of these materials. So future observations with Europa Clipper can help us discern what is that contaminant salt making Europa's surface red. Recent work by Kevin Hand and others shows that sodium chloride, when irradiated, turns a brownish color. So that's definitely an interesting potential candidate. Europa being bathed in the Jovian magnetospheric environment means charged particles are slamming into Europa at KeV and MeV energies, especially into the backside of Europa as they rotate with the 10-hour period of Jupiter's rotating magnetic field. And so we would expect surface materials to be altered by radiation. An exciting way to get at the composition will be through mass spectrometry, and Europa Clipper has a mass spectrometer to get at the constituents that are knocked off of Europa by sputtering and other process, maybe by plumes, as we'll talk about briefly. The ice shell of Europa, we think, is convecting. I alluded to that in Sam Howell's illustration there. And these lenticulae, which is simply Latin for freckles, these dark spots, may be places where indicating convection of the ice shell below. The one analogy is salt domes on Earth, similar size and spacing in some areas as shown here. So that warm ice shell may be convecting above Europa's ocean. The hard part is getting convective upwellings all the way to the surface because that surface layer is so cold and stiff. This is an illustration by Amy Barr. Let me see if I can get it to run here, of ice convection. Here the red stuff is warmer, this is opposite Sam's coloring, and the cold is blue. And you can see that, assuming a Newtonian rheology here, warm plumes are rising up, but they have a lot of trouble getting any higher than this cold, stiff, stagnant layer near the surface, the upper third or so of the ice shell. So it's going to take something else, some other rheology, perhaps there is buoyancy because there's salt in the ice shell and salt melts out, and then the plumes can rise chemically buoyantly through the stiff upper layer and to the surface. It's still a problem in Europa geology, trying to get that warm material up and out. Oh yeah, analogous to a lava lamp, that's in the upper right corner there. It takes about 10 to the 5th years by these models for material to get from the base to the surface, by the way. That leads us to the chaotic terrain at Europa, places where the surface has broken apart. It kind of looks like icebergs floating in a sea, but again, it's really hard to have liquid water at the surface of Europa where the average temperature is about 100 Kelvin. So it may be that we're seeing evidence of warm ice making it to the surface and blocks disintegrating above that layer. So Connemara chaos shown on the left, and the upper right, Thera macula, another chaos where the region has broken up and you see these ice blocks and a matrix of material. One idea is that there's melting within the ice shell and that the chaos forms by collapse above a melt pocket. If you form melt, the volume decreases and the surface could collapse into that melt pocket. So perhaps chaos regions are telling us that there is or was liquid water in the subsurface in those regions, and that's something we can find out with Europa Clipper. In 2014, Hubble observations of Europa in looking at hydrogen, Lyman alpha, and oxygen suggests there might be activity at Europa. So in the image on the left there's a glow on the limb, both in Lyman alpha, hydrogen, and in oxygen at the same place as seen by Hubble observations over 6 successive orbits, the morphology changing a little bit. And the idea is that Europa may be sporadically erupting H2O, and that is then broken apart into hydrogen and oxygen and excited for us to see with the Hubble Space Telescope. The problem is the signal to noise is something like 1 to 2 in these observations. It's later observations by this group, by others, don't see the glow. There were some observations of Europa against Jupiter that suggest absorption seen along the limb. There are other, there's some more recent work that suggests that might be noise in the image. So it's somewhat uncertain, but a tantalizing possibility that Europa might have plumes analogous to Enceladus that erupt. And if that's the case, the Europa Clipper could presumably fly through such plumes, if they're not too dusty, and scoop up some of that material and analyze it and tell us what's in the subsurface. Now, unlike Enceladus, if there are plumes, they might not tap the ocean. Higher gravity means fractures can't penetrate deeply at Europa. Perhaps instead they tap subsurface reservoirs, lakes, or other water bodies. So in summing up the Europa geology part of this talk, it leads us to the question of, does Europa have the ingredients for life? So the summary illustration on the right here of Europa's ice shell, not to scale again, ice shell maybe about 20 kilometers thick, ocean something like 80 kilometers thick. There is a probable saltwater ocean implied by the surface geology, the magnetic field, and thermal modeling. Surface geology, i.e. the fact that it cracks, some type of fractures I didn't discuss here, and the idea of non-synchronous rotation of the ice shell suggests decoupling of the surface from the interior, which is consistent with an ocean. Impact craters are consistent with an ocean. There may be liquid water bodies within the ice shell, lakes within the ice shell produced by local melting. Maybe there is geysering and plumes. So Europa almost certainly has liquid water, the first key ingredient for life. What about the right chemistry for life? Well, the ocean's in direct contact with mantle rock, promoting leaching of materials into that ocean. We see dark reddish materials on the surface containing salts that were potentially derived from that ocean, suggesting communication to above. Whether Europa has the right chemistry for life depends on, does it have the right elements, carbon, hydrogen, nitrogen, oxygen, etc., probably delivered by asteroidal and cometary impacts over time. The key uncertainty in terms of whether Europa could support life is, could that ocean have the chemical energy necessary for life? So we're not talking about photosynthetic life at Europa. We're talking about potential for organisms that live off chemical reactions, chemical energy that might sustain life. Well, at Europa, the surface is irradiated, as we were alluding to earlier, and that creates oxidants, things like peroxide and formaldehyde, and for that matter, O2 that can stay behind in bubbles as the hydrogen disappears. As irradiation hits the surface, knocks apart H2O, causes radiolysis, formation of things like formaldehyde and peroxides, and hydrogen is generally lost. If the oxidants can get into the ocean, that's a wonderful potential fuel for life. Then you need the reductants. Well, if the mantle is tidally heated and warm, then there might be hydrothermal venting, circulation and venting at the base of Europa's ice shell. But even if not, just mantle, rock, and water reactions create reductants through serpentinization. So there's almost certainly enough reductants. The limiting factor is probably the oxidants. We need to understand if and how materials can get from the surface of Europa into the ocean. And to understand what the ocean properties are like, we want to know if oceanic material can get to the surface. So that kind of sets up where we go and our big questions for the Europa Clipper. So Europa Clipper goal and objectives were honed over a decade and a half or so as we tried to get this mission going. Some of that time along with our colleagues from Europe in considering the goals and objectives for the JUICE mission. The overall goal for Europa Clipper is to explore Europa to investigate its habitability. The objectives break down into ice shell and ocean composition and geology. In terms of the ice shell and ocean, we want to characterize that ice shell any subsurface water, their heterogeneity, the properties of the ocean, and the nature of the surface ice-ocean exchange, because that gets into issues of habitability, oxidants into the ocean. Composition, we want to understand that composition of Europa's ocean as it tells us about habitability. And in terms of geology, we want to understand how these bizarre surface features form, what's the role of liquid water. We want to especially concentrate on areas of recent or current activity, and then characterize high science interest localities. There is a fourth unspoken objective, if you like, that cuts across all these, and that's recent activity. Is Europa active and how? And also, we want to use the Europa Clipper mission to feed forward to future missions and characterize the surface at high resolution to be able to put a lander there in the future that would really go after the question of, is there life there? We're a habitability mission. A potential future lander could be a life search mission. Our science investigations are summarized here. The in situ with the orangish circles and remote sensing with blue. Let's start with the remote sensing first, because you'll hear some of the alphabet soup of the instrument names in coming slides. Europa UVS, that's our ultraviolet spectrograph run out of Southwest Research Institute, Kurt Rutherford, PI. That's our Plume hunter. ICE, Europa Imaging System, is a imaging suite, camera suite of a narrow angle and a wide angle camera to map Europa's landscape in color and in 3D at a variety of resolutions, from global scale all the way down to 0.5 meter per pixel with the narrow angle camera. MISE is the infrared spectrometer. ICE, Zibby Turtle, APL, is the PI. MISE, the infrared spectrometer, Diana Blaney at JPL, is an infrared spectrometer with high spectral and spatial resolution to get at the chemical properties of Europa's surface, try to identify those salts, and hunt for any organic materials. ETHEMIS is a thermal imager to look for hotspots. Phil Christensen, ASU, is the PI. And also to characterize the thermal inertia and therefore the blockiness of the surface, again, to feed forward to a potential future lander. REASON is our ice-penetrating radar. Don Blankenship at the University of Texas, Austin, is its PI. It's being built at JPL to probe the interior. I've talked about the ice shell and whether there's liquid water within and the importance of circulation of that ice shell. And the radar, ice-penetrating radar, will be able to send signals that bounce off liquid. That ice is transparent to long wavelength radar, so that radar signal can go right through cold, clean ice, bounce off liquid water, and back to the spacecraft where we can detect it. Problem is, Europa's ice is probably not cold and clean, at least not everywhere, so we'll have to pick out windows where we potentially can get down to liquid water, at least subsurface lakes, or possibly even all the way down to the ocean. MASSPEX is mass spectrometer. The PI is Jim Birch at Southwest Research to get at the composition of neutral gases around Europa. SUDA is a dust analyzer, also a type of mass spectrometer to look at impacts of microscopic dust onto plate, and from that we can get at the composition of the solids, the particulates at Europa that are knocked off of the surface by micrometeorites. Sasha Kempf at University of Colorado is the PI. ECM is the Europa Clipper Magnetometer. Margaret Kivelson is the team leader. Rather than a PI, it's a facility instrument. She's at University of Michigan and UCLA to, as I mentioned, get at the thickness and salinity, conductivity of Europa's ocean. And in order to understand that magnetometer signal, we need to understand the plasma environment around Europa using PIMS, Faraday cups that measure the temperature and composition of the plasma. And last but not least, down at the bottom, gravity and radio science. A team was just added very recently to use our telecommunications system in order to get at the interior structure of Europa through gravity. Because analogous to the magnetometry, making many, many flybys here on the order of 50, we can not just tell the interior layering, but look for time-varying effects as we fly by Europa in various parts of its orbit around Jupiter. On the left is an illustration of our spacecraft. It is solar powered, as is JUICE. We have 5 panels on each side for about 100 square meters of area. On top is the 3-meter high gain antenna. It's body fixed. Coming off the back is the magnetometer boom with 3 flux gates. That boom will deploy, as will the arrays as we're leaving Earth. The long antennas hanging off the solar arrays are the HF antennas, the high frequency radar antennas to plumb deeply and search for an ocean. There are 4 other VHF antennas hanging off the solar arrays that will have higher resolution at shallower depths, and working in tandem will get at where that water is within Europa. The remote sensing instruments are generally down-looking. We're seeing the spacecraft in its flyby configuration. The solar arrays are articulating, I should say. They generally follow the sun, except during a flyby when they're fixed and we run off battery power. The remote sensing deck is facing down at that time to see the surface, while the in situ instruments are facing forward. The goal of the Europa Clipper is to be able to use all of the instruments at the same time. The challenge there is gravity, and we have fan beam antennas and low gain antennas situated around the spacecraft, so that we're seeing one of the antennas during some point of each flyby for about 2/3 of the flybys, so that all the instruments can operate at the same time. For those who know of or were involved in Cassini, realize the issues of time sharing the spacecraft if all the instruments cannot observe at the same time. On the right is an illustration of our trajectory, and these orbital paths are color-coded based on the radiation exposure. So the cooler colors are earlier, less radiation exposure, the warmer, more later in the mission, up to 3 megarads, which is our design. Let's take a look at the trajectory in motion here. The first few orbits are long and looping as the orbits are shaped by encounters with Europa, Ganymede, and Callisto. And we come down into a resonance with Europa, such that we're flying by Europa every 4 times it goes around in its orbit, a 4-to-1 resonance. And in the beginning of the mission, we're encountering Europa on the lit side of Jupiter, the sunward side of Jupiter, and we're encountering it on the outside of its orbit to see the anti-Jovian hemisphere and cover that well. And later in the mission, we'll start encountering Europa on the other side of Jupiter to see now the sub-Jovian hemisphere of Europa lit. And in that way, we can use flybys to see most of Europa. And this illustrates that coverage for representative tour. So we're coming around the trailing hemisphere, no close approach flybys, and now we're coming around to the anti-Jovian hemisphere, where there's a concentration of flybys, color-coded by altitude here. The red and the orange are the closest. We get as close as 25 kilometers from the surface. There goes the big guy in the background. And we can't make close flybys of now the leading hemisphere, and we saw the trailing before, because that would imply we're kind of crashing into Europa, which we don't want to do. And then as we come back around to the subjovian, we see lots of close approaches there as well. So we're seeing the leading and trailing hemispheres from afar. So for example, we can use our narrow angle camera from afar to map those hemispheres, and then we're staring Europa in the face during these other flybys. We're getting a web of flybys around Europa at various longitudes and latitudes. And on the right, you can see example coverage maps for the various instruments. For reason, we're seeing the ground tracks and their crossover points. For ICE, reason the radar. ICE, the cameras, we're seeing example coverage maps where the highest resolution is near 0 and 180, the subjovian and antijovian points, and lesser resolution near 90 and 270. Ethemis, the thermal imager, you can see that also illustrated pretty clearly. Europa UVS and MISE. Sorry, the thermal instrument Ethemis, Europa UVS, the ultraviolet spectrometer, and MISE, the infrared spectrometer. So we've been carefully trying to balance the needs of each of the instruments, again, so that we can look together, not waste time when instruments are getting doses of radiation with every flyby, and ensure that the instrument suite can look together, which allows for the best synergistic science, allows us to look across the instruments best. We'll take a look at another cool movie here, an example flyby from the Europa Clipper. This illustration is a little old. It's showing the old radar antennas. The VHF antennas have changed shape. Also, this indicates IceMag, which was our magnetometer, which has changed to a facility magnetometer now. And that new magnetometer requires spacecraft rolls. They're not yet in this illustration, but it will give you a feel for how we use the spacecraft to look across all with all the instruments simultaneously. In the lower right, there's an illustration of the orbit of the spacecraft and of Europa itself. So let's take a look at an example flyby. Oh, a couple more things. On the top, you're going to see which instruments and modes are active, and in the lower left, but the various instruments will light up, if you like, and you'll know which ones are active by looking there as well. So here we go. Europa is on the right center, and we're doing an ultraviolet scan. We're fixed relative to the spacecraft and coming in on Europa. The solar panels are oriented toward the sun to charge up before a flyby. The magnetometer and the plasma instrument are active. That was a calibration of the thermal instrument. We roll around to place the nadir deck toward Europa, here looking with the thermal instrument, an occasional infrared spectrometer observation. That's our joint scan. 3 instruments which need to scan across Europa with the spacecraft motion. So we scan the whole spacecraft and run all 3 instruments together. As we're coming in, you'll see the spacecraft roll to its flyby position to place the radar antennas in the proper position for a flyby momentarily. You can see there it goes. You can see the occasional flash of the wide-angle camera doing a context image, and then all instruments on as we fly by Europa, which surprised our avionics folks and in terms of the amount of data that is flooding from the instruments over to the flight computer and data storage system. And then we do the same backwards as we pull away from Europa. The goal is to keep operations as simple and repeatable as possible. And here's that joint scan again, ultraviolet spectrometer, thermal instrument, and the narrow angle camera at the same time. And then we get ready to turn back toward Earth and start broadcasting the data back. So again, a change that's occurred since is that we're going to need to roll the spacecraft for our magnetometer, which takes up a little bit of observation time away from others, but not nearest closest approach. We've been careful to place those in the appropriate place within the magnetic field and to squeeze them into the timeline. So that's what we're doing at Jupiter. How do we get to Jupiter? We're still not sure. NASA hasn't yet chosen a launch vehicle, and the launch vehicle will determine the interplanetary trajectory, how we get there. The principal candidates are direct to Jupiter, and we could do that with the SLS, the Space Launch System, and that would be about a 2.5 or 3 year time of flight to Jupiter. And so if we were to launch in late 24, mid to late August of 24, we could get to Jupiter in between March and August of 27. But there is another option, and that would use a commercial launch vehicle such as the Falcon Heavy to do a Mars-Earth gravity assist. So if we launch in late 24, in this case October, we would do a Mars gravity assist in February of 25, an Earth gravity assist in December of 26, and then off to Jupiter, arriving in 2030. And then again, about 1.5 years before we start the resonance with Europa. So we are anxiously awaiting a decision from NASA on that issue. In the meantime, hardware is being built, and boy, is it exciting to see this spacecraft come together. Unfortunately, during COVID, I personally haven't been able to go out and see these things, so I'm living vicariously through the photos, but it's just so exciting that it's coming together and will be assembled at JPL. The solar arrays might be delivered directly to the Cape. We're looking into that timing. Solar arrays being done by Airbus, same as JUICE. Here's the high gain antenna reflector being completed. The nadir deck on which those nadir facing instruments is being machined. The propulsion module, which is really the bus of the spacecraft, being assembled. And some of the instrument hardware. Some of this is flight hardware, some of this is engineering models, some of this is prototype hardware, but it's coming together. That's the lens of the MISE infrared spectrometer that's going to Jupiter. That's the flight model housing of the ultraviolet spectrometer and the PIMS collector assembly and the ETHEMIS telescope housing. Engineering model of the narrow angle camera, engineering model of the mass spectrometer, pseudo dust collector engineering model in a dust chamber set up at the University of Colorado, Pathfinder version of the Clipper magnetometer sensor, and a lower right there, deployment movie of the VHF antennas. There won't be a person. There'll be a device that pulls a pin to allow those antennas to deploy. So I really want to thank for this talk the team itself, the Europa Clipper Project Science Group. There are currently 131 PIs, team leaders, co-Is, and those of us in Project Science, color-coded here. There's a picture from our 8th Project Science Group meeting at JPL back in February. We could still get together in person. Our project manager and deputy project manager in front, Jan Chodis, our project manager, and Jordan Evans, our deputy project manager. So this photo includes some of the engineering team. Oh, and our mascot, the monolith. There are now 4 because everywhere the team meets, we need a monolith. We had to have virtual monoliths for our last team meeting, unfortunately. Here's our website. Check out more about the mission there. And I thank you for your time. I'm very happy to take questions.
Bob, thank you so much for such a fantastic seminar. That was really superb, and thanks for bearing with our problems, etc. So open it up to questions. You can freely ask. We're different to the Teams live meetings, so just feel free to speak up. And if you want to send chat through, I can line people up. And we will also have, Bob will be available later as we go on to chat for a short period. So please, any questions?
I can see one, Sanjeev, in the chat. Do we have any sense of how warm the subsurface ocean might be as at its warmest?
At its warmest, well, melting temperature, right? So, I mean, the exact temperature will depend on the salinity and the thickness of the ice shell, but you know, it certainly approaches 0 degrees C near the ice-ocean interface, or the melting temperature might be depressed to -10 C, something like that, depending on the salinity. So it's a very Earth-like ocean, if you think about it, and even the pressure at the bottom of a 60, or I guess it would be 100-kilometer depth beneath the ice shell on the ocean, because the gravity of Europa is 1/7 of the Earth. It's like the pressure is similar to the deepest parts of the Earth's ocean at the base of Europa's ocean.
So we're getting a lot of questions coming in. So I've got a question here from Ewan Furness. Are the potential within shell water pockets produced by decompression melting, or is it some other process without an Earth analog? Is the shell...
Sorry,
carry on.
Go ahead. Sorry.
Oh, carry on, answer that one first. And there's a
okay. So there isn't decompression melting on Europa, it's decompression freezing, right? Because ice, the slope of the melting curve is opposite for ice. So the thought is, right, it's kind of speculative. There's evidence for liquid water at the surface. How it gets there is speculative. And because heat is concentrated in warmer ice, it could be that there is a thermal runaway to create melt pockets as related to concentrated tidal heating. But it takes a lot of energy to do that. So it's really not clear whether it's geophysically plausible to get melt pockets within the ice shell. But the geology suggests they may be there.
Yeah, I had a follow-up question to that one. Is the shell less compositionally variable than on Earth? And if so, is the melting likely to be more complete?
Okay. I would certainly imagine that the composition is less variable because you just don't have the variability of composition in an ice shell. You might get, you know, some more salty in this area and some different kinds of salts in that area. But given that the ice shell is formed from an ocean that must be reasonably well mixed, I would expect it to be pretty similar from place to place. And so far, the spectra that we have from Galileo suggest that. But of course, we need and find out whether there could be plumes of material that make it from the ocean to the base of the ice that might implant some compositionally different stuff from place to place, I guess remains a question.
Okay, so I had a question, will the EIS instrument be able to take color images?
Yes, both the NAC and the WAC, narrow angle camera and wide angle camera, have color stripe filters, and I believe it's 6 of them. And so as long as it's scanning with the direction of motion, if it's in framing mode, it can't do that in color, but in push broom mode, both cameras can do both modes, then we can do color imaging.
Okay, so Adriana asks, what is the expected variation of temperature on the surface?
About 120K in the warmest low albedo regions near the equator to about 50 Kelvin at the polar regions. So there'll be variations related to how bright the surface is. So, maybe it's 10 or 20K variation between the brightest and darkest stuff near the equator, and it's pretty much all frosty and bright at the poles at about 50 Kelvin.
Okay. Hans asks, how close will the Clipper get to the surface as currently planned?
Some of those close flybys are 25 kilometers. Turns out the instruments are mostly optimized. The remote sensing instruments, including radar, are optimized to about 50 kilometers altitude. For the mass spectrometers, dust detector and mass specs, they'd like to get lower, especially for the dust detector. So we have some 25-kilometer flybys planned, a bunch of 50 kilometers, and some higher up at 100 kilometers. We're trying to find that balance to optimize the science across the instrument suite.
And there was a question related, was if there are bacteria in the plume, will you be able to catch them with the dust detector pseudo?
Interesting you asked, and Mark Septon is lead author on a paper that suggests that from mass spectra, we might actually be able to determine if there is life. So I view that as somewhat speculative. We'd have to A, have a plume, B, have abundant organisms in that plume, and sample it with the mass spectrometer. So it is not out of the question, but in general, the mission is going after habitability, and the best case scenario, it's not out of the question that we could get some indicators of signs of life if they're plentiful.
Of course, we would love all of that. It's always the same. So some more student questions. So Thanos asks, with JUICE and maybe IVO, if selected, there could be 3 spacecraft at the Jovian system at the same time. What are the opportunities for synergistic science?
Yeah, we haven't yet been thinking about IVO and implications there. I'm not sure of its potential arrival time, but in terms of JUICE, especially if we were to go on a commercial vehicle, we'd be arriving at a similar time, and the mission that evolved into Europa Clipper and the JUICE mission were born from conversations between European and US scientists, and then we went our own ways. And as soon as we get a launch vehicle and arrival date confirmed, I am hoping we can get back together more formally. But in the meantime, there have been informal conversations with JUICE scientists of the kinds of things we could do in the Jupiter system. One of the very exciting ones, and presumably apply to IVO as well, is to understand the magnetosphere at multiple places at the same time. So to understand how plasma and magnetic effects ripple through the magnetosphere of Jupiter. There'll be great synergies or complementarities, even if we're not there at the same time, of understanding Ganymede in detail and Europa in detail. There's the opportunity for one spacecraft, actually with very similar ultraviolet instruments, to observe from afar while another is in situ at the satellite. So really exciting potential of the 2 spacecraft in the system together. And again, potentially 3.
Excellent. Okay, so we had another student question. How long-lived do you think the melt pockets on Europa are?
I think theoretical modeling says they can be there from the order of 1,000 years. So it's plausible that some of the younger chaos regions, maybe there's still melt down there today. Again, if we can figure out how to make that melt in the first place. This recent paper came out just a few weeks ago by Steinberger et al. Suggests at Manannan, at the time of the impact, there was a melt pocket formed that one should be gone by now because that would have been millions of years ago. But perhaps there are some chaos areas or some ridges, if there's melt along those ridges, where the melt might still be there today. Of course, something else about Europa that I didn't mention, we don't know that Europa's geology is steady state. Europa's surface age is on the order of 60 million years, but what if Europa had a burst of activity and today it's relatively dead? So it's plausible that that the activity has waned over time, as some have suggested based on the stratigraphic relations that we see at Europa.
Cool. So we have another question here. So has there been any, so getting a lot of questions, so we're tiring you out, Bob, but thanks for taking all these fantastic questions. Has there been any analysis, perhaps considering thermodynamics, to figure out which possible compositions have energy to support life?
Yes, not my area of expertise, so I'm not going to be able to rattle them off, but so methanogenesis is a possibility. Methane plus water produces carbon dioxide. There are some sulfur reactions. If the person asking that question can drop me an email, I can send my list of the ones that have been suggested as might be kind of first order reactions to watch out for.
Great. Well, I think that's it from questions at the moment. I think we'll just have a little bit of free time afterwards if you want to hang out, Bob, and other people want to ask informally, personally questions. But I'd like to draw the seminar to a close, and I'd just really like to thank you so much for such a fantastic presentation. That's such exciting science coming up. It's really superb and great, loads of great questions today. So I'd like to get everyone to give a virtual thank you to Bob, please, for this fantastic seminar. The seminar has been recorded and will go up on the ESC YouTube page. So there's a link on chat there. And we've also posted a link to Bob's paper in Nature Communications on the mission that came out this year. That's a great place to go to for this. Next week's seminar is going to be, let me just find the details here, 3rd of December. Oop, I've lost the link. Hold on a second. I do want to remind you about this. It's a geoengineering seminar. It's on the 3rd of December. Sorry, I've lost the link in my email, so I can't tell you who exactly is, but come to that. And Bob, if you want to take a few minutes just to get a drink or something else, we'll just leave this channel open for questions, and people can just informally ask rather than putting it in chat.
That sounds good.
Thanks everyone for joining, and thanks again, Bob.
Thank you so much.